Hey everybody. So welcome to lesson 2 of solving trig equations. Yesterday, what we focused on was kind of two parts. We looked at the graphing portion, so thinking about how to solve by graphing. You've got your y equals, or your y1 on the left side, y2 on the right side, trying to find the intersection point of those guys. Remember, when you try and find the intersection point, though, it's just the x value or the theta value that you're looking at. Then we started looking at it algebraically, and we were dealing with what I would call linear equations. Today we're going to kind of go a little deeper than that. We're going to look at nonlinear. So we're going to look at degree 2. We might throw in a degree 3. But really, again, like I said yesterday, what I want you to focus on is what looks familiar. What are these things that I already know? Because some of these questions that we're going to go through today, if you just look at the whole thing, it can look rather intimidating. But what I need you to see is piece by piece, it's a bunch of little steps, and you actually know how to do all of those little steps. You know how to factor. You know how to use your unit circle to find an angle when you're given a trig ratio. It's just that all of that stuff is happening all at once, and that's what makes it look rather intimidating. So don't stress about it, just take it step by step, little by little. So as a review, first question we're going to ask ourselves here is solve for sine c equals cosecant c in the domain c is somewhere between 0 and 2 pi. So there's a couple different ways we can go about doing this. I might take a look at this first and take a look at cosecant, flip it so that it's 1 over sine c. Because that's something I can do, and that's something that looks a little bit more familiar with me. Then I also have the same trigonometric ratio throughout the whole equation. So now I can probably do some math to simplify that. One thing that we do want to think about here is restrictions. Now that we have a sign on the bottom, sine of c can't be 0. So one of the very first things you want to write there, sine of c can't equal 0. Well, now you're saying, well, where does sine of c equal 0? So we go back to our unit circle. Calgary Stampede, sine is your y value. Where does the y value equal 0? The y value equals 0 at 0 pi, 2 pi. So what we would say here is c is not allowed to be, remember the very first positive is 0, so we don't actually state 0 plus the period of repetition, we just do the period of repetition. So that would be pi n, where n is a member of the integer. So the first thing I would want you to write there is c can't be pi n, where n is a member of the integers. Now, I think what I'm going to do first is multiply both sides by sine. What that does is it ends up with a sine squared on this side, and then 1 over sine c times sine c over sine, 1 over sine c times sine c just gives me the 1. So now I can actually solve this. I can divide both sides by 4. I can take the square root. That'd be plus or minus 1/2. Please, please, please remember, still in grade 12, one of the biggest mistakes I see is that kids, when they're taking the square root, they don't, or they neglect to say that the answer is positive and negative there, and then you lose half of your final answer, so don't do that. So sine of c equals plus or minus 1 over 2. So we're looking for, on our unit circle, where sine of c would equal plus or minus 1 over 2. Remember that if it was just plus 1 over 2, there'd be 2 answers, because sine is positive in quadrant 1 and 2. If it just said negative, there'd be 2 answers, because sine is negative in quadrants 3 and 4. Now that it's plus minus, essentially it's that reference angle in every one of the 4 quadrants. So you end up with pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. The other thing to think about there, or the other way you could have done this, I'm just posting an alternative method. We could have gone back to the original question where I had already multiplied by sine and just brought the 1 over. Then we could look at it as a quadratic and factor it. That's a difference of squares. So we'd get 2 sine c plus 1 times 2 sine c negative 1. And then that again would give us sine c equals negative 1/2. And sine c equals 1/2. So it doesn't really matter which way you do it, you're still arrive at that final answer. The second one here for review is cosecant of theta. is negative 1.57. So reminder, we probably don't want to deal with cosecant. We probably just want to switch that right to sine. And if we flip it right to sine, we just switch the ratio. So now I'm going to write it as sine of theta equals negative 1 over 1.57. So now I'm going to get a reference angle from there. I'm going to arc sine the ratio, but remember, when you arc sine the ratio, you're only arc sining the positive version, and that would give us a reference angle of 0.6905. Then I apply the cast rule and think about where is sine negative. Sine is going to be negative in quadrant 3 and 4. So if I'm in quadrant 3 or 4, if that's my reference angle in quadrant 3 or 4, my first answer is going to be pi plus that guy. So that ends up being 3.8. And my second answer, the one for quadrant 4, ends up being 2 pi minus the reference angle, which gives me 5.6. Once I'm dealing with more than one solution, I usually will write in solution sets, which are the squiggly brackets, the set notation brackets. And again, we write them in ascending order, 3.8 and 5.6. Okay. Again, just like in the last example, there are restrictions on that guy. It's the same restriction because I was talking about cosecant again. C would not be allowed to be pi times n, where n is a member of the integers. These guys are not part of those restrictions, so they're viable solutions. Okay, so a nonlinear equation is when the degree is not equal to 1. If it was a linear equation, it would be equal to 1. In 20-1, when we had an equation that was of degree 1 or larger, we typically tried to, that should say degree 2 or larger, we typically tried to factor it, and that's the same thing we're going to do here. It's the same idea here, we're just dealing with primary trigonometric ratios. Okay, so just a quick review before we get messy and throw in some trig ratios. Your laws of factoring, now depending on what teacher you had, depending on how you went through grade 10 and 11, learning how to factor, there's a bunch of different ways to factor. I don't care which way you factor, as long as you can factor and show me your work. You should be able to get down to x squared plus 4x minus 5, factors into x minus 1, x plus 5. Now, remember, you can't go factoring unless it equals 0. And now that we have the factors there and it does equal 0, we have what's called the zero product principle. Either this factor here is 0 or this factor here is 0. So x minus 1 either gives me the 0 or x plus 5 either gives me the 0. And that's where I get my two values for x, either x equals negative 5 or 1. In the other one, I've got 2x squared plus x minus 1. So I'm going to walk you through a decomposition here. I'm looking for two numbers that multiply together to give me negative 2. 2 times negative 1, the outside guys, and add together to give me 1. Those two numbers happen to be 2 and negative 1. So what I did was I decomposed, I split my middle guy up. The 1x, I split it up into 2x minus x. Now I factor the front 2 and factor the back 2. I can take out a 2x from the front 2, and that leaves me with x plus 1. Then I can take out a negative 1 from the back 2, and that leaves me with x plus 1, which causes my heart to go pitter-patter because I have the same thing in the brackets. X plus 1 is now a common factor. It can come out, and I'm left with 2x minus 1 as my other factor. So I've got 2x minus 1 as one factor and x plus 1 as the other factor. Either one of those, this is now back to the zero product principle, either one of those could be 0, so x ends up being negative 1 or a half. Okay, essentially that's all we're doing today. That's all we're reviewing today. We're just going to throw in some trig functions at the same time. So the questions for all of these will be solve the following on the given domain and then state the general solution. So we're going to work with the domain given, and then we're going to conclude how would we write this for every possible solution. So for the first one, sine squared theta minus 2 sine theta minus 3 equals 0. Now, again, just take a step back. It looks a little intimidating, but I just want you to see it's a quadratic. And if you don't see that right away, let's make sure you see it. Let's do a substitution. So we're going to say let A equal sine of theta. That is totally okay to do as long as you state the substitution you're making. Okay, so now I can rewrite it as a squared minus 2a minus 3 because I let A equal theta. So every time, I let a equal sine theta. So every time I see sine theta, I could replace it with an a. Okay, well, this is just a factoring question now. This is just like the slide I just gave you, looking for two numbers that multiply together to give you -3, add together to give you -2. So that guy factors into a minus 3 and a plus 1. If it factors into a minus 3 and a plus 1, that means a could be -1 or 3. Now, if you're going to do that substitution, here's where you have to remember that a is not a anymore. You have to substitute back, or else you're losing what you're doing. So a is actually sine of theta. So now that we've got values for a, we put sine of theta back. We say sine of theta equals -1 and sine of theta equals 3. Well, now I solve for each of those. Sine of theta equals -1. Where on my unit circle do I have a y value of -1? There's only one spot there, and that's 270. The second one says sine of theta equals 3. Well, that's not possible. I can't have sine or cosine ratios outside of the -1 to 1 range if you think about a sine graph, okay? None of those sine ratios are above 1, and none of them are below -1. So sine of theta equals 3 renders no solution. Make sure you state that, though, because we need to know you're aware that that doesn't do anything, that there's no solution. If you just leave it, we're not sure if you just missed it or if you were avoiding it or what you were doing. So make sure you state no solutions. So there is only one here, it's 270. Now, the general solution, it'll be 270, and it'll be every time a coterminal angle of 270 comes around. So we would say 270 degrees plus 360 degrees n, where n is a member of the integers. Now, depending on the book you're using, depending on the answer key you're looking at, even when you look at our answer key for the homework today, we will go back and forth. Sometimes you'll see us use I, sometimes you'll see us use Z. They both refer to the integer family, so don't let that stress you. Okay, so the second one, 4 sine squared theta minus 3 equals 0. Okay, well, think about all your algebra skills. You're going to want to add 3 to both sides. You're going to want to divide by 4. Then you're going to want to take the square root. So that's adding 3 and dividing by 4. When I go to take the square root, remember, it could be plus or minus. So I have plus or minus root 3 over 2. I'm now back to my unit circle. That is something that I should, at this stage of the game, be very familiar with looking at and saying, hey, that is on my unit circle. If I'm looking for the sine of theta to equal root 3 over 2, I'm at pi over 3 and every reference angle of pi over 3 after that. So I end up with pi over 3 in every quadrant. So pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So that's my answers from 0 to 2 pi. Now, if I want to think about the general solution, I want to try and say this in as few steps as possible. So maybe I want to look at, hey, how do I go from pi over 3 to 2 pi over 3? Because maybe I could just say, I'm just going to go pi over 3 plus pi over 3n. That doesn't work, because in order for that to have worked, the 2 pi over 3 would then have to add pi over 3, and I'd get 3 pi over 3, or pi, and that's not there. That's not part of my solution set. So now, usually what happens after that is I try and start pairing things together. For this guy, let me just put a highlighter on here for you. I compared these guys together, and I compared these guys together. So I can go pi over 3 plus pi n, because that's like pi over 3 plus 3 pi over 3. That gives me 4 pi over 3. And 2 pi over 3 plus pi n. And in both of those instances, n would be a member of the integers. So the general, so there's my solution set. Sorry, I got carried away. I forgot to write it in the solution set first. And then there's my general solution. So pi over 3 plus pi n, and 2 pi over 3 plus pi n. Okay. Next guy we're going to tackle is cos squared theta minus cos theta equals 0. Now, again, here we go dealing with a quadratic. Maybe you want to factor this. Sorry, you do want to factor it. That's not what I meant to say. Maybe you want to do a substitution. Like maybe you want to say cos of theta equals a first, and deal with it that way. That's totally fine. I'm not going to do that anymore, but if you want to do that, you are more than welcome to do that, okay? I'm just going to take a look at this and say, hey, cos of theta is common to both of those terms, so I'm going to factor out a cos of theta. That would leave me with cos of theta as one factor, and cos of theta minus 1 is the other factor. I'm right into my zero product principle. Either I can say cos of theta equals 0 or cos of theta equals 1. Well, where does cos of theta equal 0? Calgary Stampede, that's the x value on my unit circle. I'm looking at 90 or 270. And then where does cos of theta equal 1? I'm looking at 0 or 360. Okay, all of those are viable options within the restrictive domain that I have. So I have 0, 90, 270, and 360. Now, for the general solution, is there a way to say all of that in as few statements as possible? That's what I'm always asking myself. In this one, I can actually do it in one statement because 0, 90, 270, 360, they're all 90 degrees apart. So I end up actually just saying 90 degrees n, where n is a member of the integers. Remember, because it would be 0 plus 90 degrees n, and I don't need to say 0 plus. Okay? All right, next guy, 2 cos squared theta equals 3 cos theta minus 1. So again, I want you to see this like a quadratic. If you want to do that substitution and say cos of theta equals a first, just so it's not as intimidating on your first go, that is totally okay. If you do that though, you have to say that statement, let a equal cos theta or let x equal cos theta or whatever. You have to communicate that you're doing a substitution, or else what you're saying won't make any sense mathematically. So it's just a matter of making sure you're clearly communicating what you're doing. I'm not going to do that. I'm just going to bring everything over and deal with cos like cos. So I brought my 3 cos theta over, I brought my -1 over, and I'm left with this quadratic to factor. Looking for two numbers that multiply together to give me 2, add together to give me -3. That would be -1 and -2. I'm going to decompose this. So my middle term gets broken down into the -2 and the -1. Factor the front 2, factor the back 2. I can take out a 2 cos theta from the front 2. That leaves me with cos theta minus 1. And I can take out a -1 from the back 2. That leaves me with cos theta minus 1. That means cos theta minus 1 is a common factor that I can pull out, leaving me with 2 cos theta minus 1 times cos theta minus 1. I'm now at the zero product principle. So this guy equals 0, or this guy equals 0. So I have two little statements to make now. The first would be cos theta equals 1/2, and the second would be cos theta equals 1. Well, where does cos theta equal 1/2? I'm at pi/3 on my unit circle, and I'm in quadrant 1, and I'm in quadrant 4, so that'd be pi/3 and 5 pi/3. Where does cos theta equal 1? I'm looking at 0. Now I'm also looking at 2 pi. I just ignored it because I knew right away, if I go back, if you see my mouse circling, to remind you, in my restrictive domain, I can't actually be 2 pi. That's why I just said 0 there. So I'm looking at 0, pi/3, and 5 pi/3 as my answer within that domain. For the general form, again, the 0 is going to end up giving me one statement, which would be 0 plus 2 pi n. So I'm just going to say 2 pi n. And then the pi/3 has to be its own statement, and the 5 pi/3 has to be its own statement. The reason I know that is because if I tried to connect them, how do I go from pi/3 to 5 pi/3? Well, I'd have to add 4 pi/3. And if I do that to the next guy, 5 pi/3 plus 4 pi/3 would give me 9 pi/3, and that's not a viable answer. So that's why I know I have to do it in 3 different statements. So my general solution would look like this. I've got my 2 pi n, that deals with the 0. I've got my pi/3 plus 2 pi n, and I've got my 5 pi/3 plus 2 pi n. A reminder, sometimes you'll see this as 2 pi n, sometimes you'll see this as 2n pi. Doesn't matter, it's the same thing. And sometimes you'll see this as I, sometimes you'll see this as z. Totally okay. They both mean the same thing. All right, good job, guys. Now we're going to get to the last one, which is tan. Tan has restrictions on it. Right away, either I want you to know where tan is undefined, or I want you to think about tan being sine of theta over cos of theta, and immediately you would tell me, hey, cos of theta can't be 0 now, because that would give me a 0 on the bottom of a fraction. So if cos of theta can't be 0, where does cos of theta equal 0? Where does that x value equal 0? That would be at pi/2. and then every multiple of pi after that. So pi over 2 plus pi n. I'd be here and here. So pi over 2 plus pi n plus pi plus pi plus pi. That's where we're getting that pi n from. Okay, now this looks scary. Well, 10 to the 4 theta is actually a common factor there. So I just factor it right out. I've got 10 to the 4 theta coming out to the front, factoring out to the front. Then I end up with 10 to the 4 theta minus 1. I'm now actually right at the zero product principle. So I say 10 to the 4 theta equals 0, and 10 to the 4 theta equals 1. Well, 10 to the 4 theta equals 0. When I take the fourth root of both of those sides, the fourth root of 0 is 0, so I'm just left with 10 of theta equals 0. Okay, where does 10 of theta equal 0? That would be at 0, pi, and 2 pi. Remember, tan is y over x. So at 0, pi, and 2 pi, I'm getting 0 divided by 1 or 0 divided by negative 1. So that gives me tan of theta being 0. 10 to the 4 of theta equals 1. Well, I'd want to fourth root that. If I'm taking an even root, just like a square root, my answers are going to be plus or minus. So I end up with 10 of theta equals plus or minus 1. Where does 10 of theta equal 1? That would be at pi over 4. And because it's plus or minus 1, I can be in all 4 quadrants. So I'm looking at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Okay, so put all that together, my solution set in order would be 0, pi over 4, 3 pi over 4, pi, 5 pi over 4, 7 pi over 4, 2 pi. Remember, I really want you to get in the habit of writing those guys in order from smallest to largest so that we're all communicating the same way. Now, for the general solution, I see this as 2 different statements. This guy here, I can actually make in one complete statement. 0, pi, 2 pi, that's just pi n. And then this guy here I can make in one statement. This is pi over 4 plus, well, how am I going from 1 to 3 to 5 to 7? I'm adding 2. So I'm adding 2 pi over 4. Just remember that 2 pi over 4 will reduce to pi over 2. So my general solution is pi n, where n is a member of the integers, and then pi over 4 plus pi over 2n, where n is a member of the integers. Okay, so that's what we're going to be working on now. Again, don't let yourself get intimidated by the questions. Everything we've just done here, you have done in smaller portions. It's just now we're putting them all together, and you guys can totally do this. So your homework, oh yeah, just a very quick reminder, this is the same slide that I gave on the last PowerPoint. Remember, do not divide out functions with trigonometric equations. You will lose solutions, and we don't want that to happen. So you're going to work your way up to 239. The other thing you're going to do, this is lesson 2. If you'll notice in our D2L, I then call a lesson 3, which is just review of solving equations. There's no additional note for that. It's just more practice on solving equations, okay? So you'll find a couple extra worksheets with answer keys posted in D2L inside the lesson 3 portion. There won't be a video for that because it's not an actual note. It's just practicing more of what we've done the same, okay? So once you've tackled all of that, the next thing we'll do together via video will be the beginning of trigonometric identities. So we'll see you for that. Have a great day, guys. Bye-bye.